Hello, my name is Berkemal Sungur, and this is my EEE102 digital design project, the self-parking car. In designing this car, as external components, of course, I use the chassis of the car, which contains 4 motors connected to the wheels. I also use 3 ultrasonic distance sensors, which are, of course, required for the parking algorithm. Here, I use the motor driver card, which converts the logic signals from the Basys to the forward or backward motion of the cars. I also used here 2 logic level converters, which are required because the echo output of the sensors are 5 volts, but the Basys pins are only rated up to 3.3 volts. And since the sensors work with 5 volts, I needed 5 volts on the car. That's why I constructed a 5 volt voltage regulator circuit. And that's how I got 5 volts on the car from a 9 volt battery. And like that, with that I don't need any external power. I just need this cable which connects the Basys to the computer. As you can see, the car finds the available parking spot and parks by itself. Now I will talk about how my code works. First of all, we have the sensor module. The sensors need a 10 microsecond pulse every couple hundred milliseconds in order to be triggered. With the trigger, the sensor sends out an ultrasonic burst and the echo signal becomes high. When the ultrasonic burst reflects back from a surface and is received back by the sensor, the echo signal becomes low. With this code, we send out the trigger signal, like mentioned before, and calculate the distance by measuring the time the echo signal stays high. Next, we have the motor driver module. The way the motor driver cards work is in the following way. If we give a motor the input of 1 0, it drives forward. If we give it 0 1, it drives backwards. The other inputs 0 0 and 1 1 makes them stop. I have written the motor module in such a way that it takes directions such as left, right, forward, or backward as input, and outputs the corresponding logic values to the motor driver card, which then drives the motors. Of course, we have the top module, which connects every module together. And lastly, we have the parking algorithm module. It was implemented using a finite state machine. And now I will present the states and the corresponding parking algorithm. State A is the hold state. No motors are active. Every other state goes to this state when reset is 1, independent of the clock. If enable is 1, it goes to state B. State B is the initial movement state. At this point, the car should be parallel to the obstacle. The car drives forwards in the state. When sensor 2 reads a distance of more than 15 centimeters, it goes to state C. At state C, the car is next to the parking spot, so it has detected it. The car continues to drive forward in the state. When the sensor 2 reads a distance of less than 15 centimeters, it goes to state W. W is a wait state. It serves to stabilize the car before direction changes, as sudden changes sometimes cause unexpected movements. Right now, the car is next to the car in front of the parking spot. It waits for 0.6 seconds and then it goes to state D. In state D, the car backs up until sensor 2 reads a distance of more than 15 centimeters. The car drives backwards in the state. When sensor 2 reads a distance of more than 15 centimeters, it goes to state W2, which is another wait state. The car waits for 0.6 seconds and then it goes to state E. In this state, the car turns right. It turns a set amount governed by the time it spends in this state. The turn-in is only negligibly different for different scenarios, and it is unreliable to govern this turn by sensor readings since they are not perpendicular to a surface through the state. Therefore, I opted for a set amount of turn in every condition, which turned out to be 0.561 seconds. So, after being in this state for that time, it goes to state F. In state F, the car drives backwards. It backs into the parking spot. When sensor 3 reads a distance of less than 13 centimeters, it goes to state G. The car turns left in state G. It adjusts itself to become parallel to the parking spot. When sensors 1 and 2 read the same distance, it goes to state H. In state H, the car drives backward. It adjusts its proximity to the rear obstacle by driving back towards it. When sensor 3 reads a distance less than 10 centimeters, it goes to state J. In state J, the car is stationary in its park position. The only way out of this state is via reset. Now you can see the entire parking process.